Thank you very much for the invitation. So I have just left, I guess, Tuesday from my place where the temperature is exactly the same as here in absolute value. And as you see, I'm confused with minus signs. And since I left Tuesday, I have slept or tried to sleep only in airplanes. There won't be any complicated mathematics. I don't think I could be able to anti-commute anything at this time. So Antoine asked me to make a quick survey, experimental survey of high-temperature superconductors, which I will do, and I will probably do just as many mistakes as I would with Grassmann variables. But anyway, since I'm not an experimentalist, I will have an excuse. So this is a mouse, not a laser. So even if I point to you, there's no danger. So it takes into account the fact that I'm sort of a little bit dizzy. And okay. So, pardon me? Do we need to be vaccinated? Probably that's the next step. So superconductivity is really a beautiful phenomenon, and I want to start with this. So this is a piece of yttrium barium copper oxide. So this is a black ceramic, and we will talk a lot about this this compound. And what is on it now is just a very high magnet with a very high magnetic field. Now, if you drop a liquid, I don't know why it's like this. Oh, when I press this. So this is a liquid nitrogen that's put on it. And now, what will happen, you think, when it becomes superconductor? Any guess? Yes. So that's the condensation energy has given the energy to go up. So you expel the magnetic field, and this is what happens. So you've converted the heat into work, but there's no problem with the second law because we have a cold and a hot reservoir. So how do I change this now? I probably need to stop it. Oh, interesting. This is where the talk ends somehow. Okay. Okay, the two most successful theories of condensed matter are superconductivity and band theory, and that's something that is discussed in this school. So for superconductivity, there are two ingredients, as you know. One is the attraction. So you take an electron, it scatters off a phonon, and then if you look at the time-reversed state, you can see this as a pair, P minus P, time-reversed state, that goes into the same pair. So you can do this coherently. And one way to see why coherence comes in is to take just the potential energy. Take the potential energy, and this is the wave function for the incoming pair, P minus P, and the wave function for the outgoing pair, P prime minus P prime. Now do just what you would do in mean field theory for the Ising model. And clearly, to minimize the energy, the phase has to be the same independently of P and P prime. Otherwise, it would average out. So the ground state has this structure where you see that n and theta are conjugate variable. So it's a superposition of states with different particle numbers, but a fixed phase. And now you can measure phase. The supercurrent comes from the phase rigidity. So if I try to change a phase somewhere, the current flows to make the phase go back to its original state. Now, band theory is the other successful theory of condensed matter. And as you know probably, one of the first success of band theory was to predict what would be a metal semiconductor. And if you have a system with an odd number of electrons per unit cell, band theory tells you it should be a metal. Well, already in 1937 or so, it was found by Bohr and Verwey that nickel oxide was an insulator instead, and Pars and Mott found the explanation. And they found that it is due to interactions. So this is a canonical example. This is temperature and this is pressure. And this is vanadium oxide. And you have a paramagnetic insulator, a paramagnetic metal. And you can go continuously from one to the other. And then there's a first order transition here. And so this is the so-called Mott transition. And I'd like to stress that the ground state is anti-ferromagnetic. So if you have strong repulsion between electrons, it can lead to this insulating state. And a signature of the fact that there is repulsion is this anti-ferromagnetic state. So this is not really a good simulation because it's really classical with, and it looks like hardcore bosons here. But I just want to show you that in the end, whoops, too fast, but in the end it looks as if it's the holes that are the carriers of current. So high temperature superconductors epitomize the failure of BCS theory and of band structure and of many more things. So that's what I want to show in this talk. First, well, if you look at TC as a function of time, so this is just has to do with what man can do, not really nature by itself. But the point is that the superconductors that were explained by the BCS theory have temperatures that never go much, well, don't seem to go above 40 Kelvin. But this class of materials I'm going to talk about, high temperature superconductors, have much higher transition temperature, and recently discovered iron oxide also. So the structure of these materials is planar in the sense that they conduct electricity well this way and badly this way. So if you look, this is the black dots here are copper, and this is oxygen. So we have a square lattice with oxygen on the links. And let me do one more thing. So there are many, many materials of this class, and what they have in common is just these copper-oxygen planes. What in between is very different from one system to the other. And what the rest is doing is really doping the planes. So this will be our roadmap for this talk. So this is temperature, and as a function of doping, doping in the copper-oxygen plane. So zero doping here means one conduction electron per unit cell. And what's on the, it's hole doping. So on the right is doping with hole, and on the left you're doping with electrons. And here at half filling, so one electron per unit cell, we have a Mott insulator in the sense that if we look, go above the Néel temperature and look in the paramagnetic state, we have a very good insulator, contrary to what the band structure would tell us. So already you see that this challenges conventional wisdom because you have superconductivity that's very close to an insulator. And as I said, there's an antiferromagnet, so there are that's a signature of repulsive forces, and we think that repulsion is not good for superconductivity. So the conventional wisdom for high temperature for superconductivity compared with high temperature superconductor, let's start with the conventional wisdom. So the conventional materials are mostly cubic, and it was thought that one should look at 3 dimensions, and that one should stay away from oxygen, from magnets, and from insulators. It was also proposed that you should stay away from theorists. Now, the high temperature superconductors have copper, so there's transition metal. Whoops, sorry, this is too fast. What's going on here? But they are layered, not 3-dimensional, and they are close. I mean, there's oxygen, there's magnetism, and there's an insulator. So they're very, very non-conventional. So the model that we will use is the Hubbard model that you already know. You've heard about that. So I will go quickly through this and just show you the band structure for the high temperature superconductors. So there's if we look just in the plane, and there's a copper and 2 oxygens. So there are 3 atoms per unit cell if we look just at this, these. And there are 3 important sets of bands. There's a band here that will be the anti-bonding band. There's a bonding band here. And the non-bonding bands are here. There's more than 3 bands, obviously. But we will focus just on this, this band here. And for most of this talk, I'm going to assume that that's the only thing that there is. Okay, so there are 2 terms. We will come back to this right away. So if there are no interaction, u equals 0, then we just hop from one side to the other. And the solution to this is you just go from Wannier states to Fourier or to Bloch states, and the Hamiltonian becomes diagonal. And you fill states like you learn in elementary quantum mechanics, and the ground state is just a direct product of these k states. If you go in the other limit where you have only interactions, then the way to minimize this is to localize the electrons, to put them on a given site. So, for example, at half filling, the ground state would be 2 to the n-fold degenerate, and the ground state would be a direct product, again, but Wannier states. And in the general case that will be concern us, these terms will be comparable. I mean, I said I would talk about experiment, and I'm talking only about theory, but it will come soon. This is just to put a general context. So in some sense, the interesting physics comes in when the state is maximally entangled, when neither the K state nor the Wannier states are good eigenstates. Now, how does anti-ferromagnetism comes out immediately from this model? If you start from the strong coupling limit, so you assume that the states are localized, and then you do degenerate second-order perturbation theory. There you admix the states like this, so there's a matrix element like this. There's an energy denominator U, and then you need to come back. So you generate an S.S term, it's a Heisenberg model, J equals 4t squared over U, and you get anti-ferromagnetism immediately. Okay, so the outline of the talk will be like this. I'd like to mention that I was at a summer school in Germany last September, and I wrote lecture notes for this. The title is Strongly Correlated Superconductivity. And so this can be, there's a whole book of this summer school that's on the net. It's free. You can find it in the usual way. And you can also, I have also put my contribution on CONMAT. So you can find it, so what I will give here will not be very well referenced, but if you look in this paper, it is done in a better way. So so this is our roadmap. You will see this very often. So I will talk about the normal state here in the whole dope state in section 3. Then about the normal state on the electron dope side. And then about the antiferromagnetic state. And about this state here that is focus of much attention, this charge density wave state that appears here. And finally, I will talk about the pseudo-gap here and how it's influenced by these states. We will see here that this anomalous normal state that I will describe is influenced by the presence of this ordered state, and we can ask the same question here. And finally, I will discuss about the superconductors on the electron and the whole dope side. By the way, if you have questions, you can interrupt anytime. It will help to wake me up. Okay. So is the normal state of high temperature superconductors normal? So first of all, I would like to, we're talking about this region now of the phase diagram. Yes? Yes. Why do they look very different? Well, you have to remember that it's not the same material. That's the first thing. But if we say, okay, we just have copper-oxygen planes, then it should be, as for the theorists, it's the same. Now, in practice, what happens is that the band parameters are pretty close, but they are not particle hole symmetric. So if I just take just a non-interacting problem, and I just do Stoner theory to find the anti-ferromagnetism, I will find an asymmetry that's similar to what is there. And then the value of u need not be the same also, and we will see that it is a little bit different. Okay, more questions? Is there a material that can be both hole and electron dope? Yes, there's a paper by Ando who claims to have a material that does that. It has a very complex, I mean, it has many, many elements. I forget, it has 5 elements or something like that. And so, I mean, my experimentalist friend tell me that they're not so sure that it is completely reliable. But that's, I think there's one. Okay, so I want to talk about some very general properties first, about what is a phase and what are emergent properties. So the simplest emergent properties is the metal by itself. If you just take aluminum atoms, they have a spectrum, a discrete spectrum. Now you put them together, they form a metal, and it becomes shiny. It does not have a discrete spectrum. So it has created a Fermi surface, and that's an emergent property. And so, for example, you can see quantum oscillations in magnetic field. If we put a magnetic field, the orbits are quantized, and you can see this in many, many physical properties. Now, many models, microscopic models, will do the same. Electrons in a box will have this, or atoms will have this, this Fermi surface. And that leads to the concept of Fermi liquid. So Fermi liquid is adiabatically connected to this idea of electrons in a box. So there are some, it's not really like free electrons, but there's the concept of a quasi-particle. And it's often hard to derive from first principle these emergent properties. For example, at strong coupling, people talk about gauge theories, fractionalizations, which I won't talk about here. But one has to keep this in mind. So the first statement is that hole dope cuprates are strongly correlated. And now I will show you the evidence from the normal state. What I mean by strongly correlated is that the quasi-particles are not there. So I start by this Mott-Yoffe-Rigel limit. So take the simple Drude formula, sigma equals n e squared tau over m. And so n in 2 dimensions, so d is the distance between planes, and kf squared. So this is the surface, the volumic density. You replace here. And now you notice that the mean free path is the Fermi velocity, so Fermi momentum divided by mass times tau. And the conductivity then takes this form. And now you see that the smallest conductivity you can have is when the mean free path L is equal to the Fermi wavelength. Right? We cannot have a mean free path that's shorter than the Fermi wavelength if there are quasi-particles. So you find that there is the smallest metallic resistivity, conductivity, I'm sorry, or the largest metallic resistivity is E squared over h bar times the separation between levels. Now this is a plot of resistance as a function of temperature. And you see for 2 high temperature superconductors, here the solid lines, the Mott-Yoffe-Rigel limit is really, you know, you go through it as if it was not there. If you look at more conventional materials like copper here, you have to multiply resistivity by 175 to see it on this plot. Now, if you do a calculation with Green's function, no assumption about quasi-particle or anything, and you compute resistivity as a function of temperature, this is done in this paper, then the blue line here shows that indeed there is saturation at the Mott-Yoffe-Rigel limit. So in the approach that we used here does not have the Mott physics, but it has everything with everything else. So you see, if there's no Mott physics, then there should be this saturation. Now, another way to see that it's strongly correlated is to look at X-ray absorption spectroscopy. So if you take a very deep hole electron in a core, like 2s level here, yes, in this case, I think it's 2s. So you come with a photon energy of 528 eV. So you extract this electron from very, very deep. then you will have, it will start to absorb energy when you can take it to the Fermi surface. Now, a semiconductor and a Mott Hubbard system are very, very different. So in a semiconductor, you have a valence band and a conduction band. So at half filling, it looks like this. So you have two end states if there are n atoms, and two end states here. And if I dope the system, then what you will get is just that the Fermi level moves into the lower band. So if I do this X-ray absorption experiment, I will get a peak when the electrons when going from 2s to here. And then if I dope, I will get two peaks, one for absorption here and one for absorption there. So this will be at lower energy a little bit. In the case of the Mott-Hubbard system, you have, when you have one electron per site, it starts to cost an energy U to put more electrons on it. So it means that instead of having two end states like this is split in two. There's a lower and an upper Hubbard band. Now if I dope, what happens? If I dope, I remove an electron here. And then if I look at the number of states where it will cost an energy U to add an extra electron, there's n-1 states now. And now at the Fermi level, there will be two states that are added, one up and down. So you see there's conservation of the states, but the contrary to here, this moves a lot. So what happens in these experiments? There are two peaks. I mean, if you look at this here, 0, 0, there's a single peak when you are at half filling here, x equals 0, so that's 0 doping. Now you do 2% doping, it goes, there's a peak that appears at lower energy as expected, and then you go on like this, and now you can try, this is too fast, but I will show you anyway. So what you're supposed to see here is that this peak grows twice as fast as this one goes down. So it really is as Mott-Hubbard physics. So this is just to say that this is a very old experiment, but there are more recent ones that show that it agrees with what's expected from the Mott, more serious calculation with cluster dynamical mean field theory. It agrees what's predicted with Mott. Now, why is it a Mott insulator where there is a thermal power? What time? Okay, I have already half an hour. I will skip some of this because I'm going a little bit slow here. Let me do the Hall resistivity. So if I look at the Hall resistivity, it should be proportional to 1 over the number of carriers. That's the Hall resistance. So if I multiply by the electron charge and divide by volume, and now multiply that, it behaves more like this picture where I had the electrons moving around, and in the end it was the holes that were doing this the action. And you can see that it's a collective phenomenon, because if you plot this same quantity, the Hall resistance times the doping, as a function of temperature, you start at 900 degrees here. You see that you reach this limit where the resistance times X is a constant around 300 degree Kelvin. So it's that things that happen on the scale of the Fermi energy. They happen on much smaller energy scale, and they have to do with correlations. Now, if you look at the density of states, also, this is measured by scanning tunneling microscopy. What you see is that, okay, this is not exactly a high-temperature superconductor, but it's the same. It has the same copper-oxygen planes, and you see that it's very, very asymmetrical around zero bias. So here it's removing electrons, and here it's trying to add electrons. So it's easier to remove electrons than to add electrons. What would an ordinary metal do? It would just be flat here, independent on that scale. So again, it's not a standard metal. Okay, now if I look at the electron dope cuprates, I will show you that they are less strongly coupled. So that goes back to your question. One of them is the value of U. And I show first evidence from the normal state. if you look at this Mott-Joffé-Regel criterion, this flattening here is around 400 microohms centimeter. And if you look here at 400 microohm is in this region, and you see that we're starting to level off. So it seems to satisfy this Mott-Joffé-Regel limit. Now, another topic that's often discussed in the context of high-temperature superconductors is quantum critical points. Yes?
So this resistivity is showed in plane resistivity.
Is in plane resistivity.
So is there any difference in the electron hole in the outer plane?
In the out of plane, I think there is also, but I don't have the data fresh in my mind.
I seem to remember that the CIC's resistivity although very insulating light, not so much.
Less in the electron dop, okay. So quantum critical point, okay. So what is a quantum critical point first? Let's start on the electron dope side here. Here you see the antiferromagnetic phase. And here it would, if you remove superconductivity with a magnetic field, you can imagine that this would continue here and that there would be a transition between a paramagnet and an antiferromagnet. So this is called a quantum critical point. Now in the electron dope system, there's strong evidence that there is such a thing. And this can be seen in many ways, and it will influence the normal state. If you look here as a function of a temperature for various dopings, you see that the correlation length, so this is the log of the correlation length as a function of J over T, and you see that for various dopings, so 14% here and 18%, so this goes to 100, so it is growing. These are old measurements, and these are calculations that we did with two particles of consistent approach that is based on weak coupling ideas. Now, if you look at the theoretical prediction for what the correlation length at the quantum critical point, how it scales with temperature, you find that it scales like 1 over temperature. This is very special because of well, this is more a question for experts, but it has to do with the way that the Fermi surface touch when the quantum critical point is reached. Because normally you would expect a power 2. But in fact, that z equals 1 is observed experimentally. Now, another manifestation of this quantum critical point is the linearity of the resistance. So if you look at the quantum critical point, the resistance as a function of temperature is linear in electron dope cuprates. It turns out it's linear also in all dope systems and in organic, quasi-one-dimensional organics. It's also the case in iron dope, in iron superconductors, pnictides. And so that it seems that there is this coexistence of antiferromagnetism and superconductivity is quite common. So this is the high temperature superconductors, this is the organic, this is the pnictides. And that in all cases, when you go down here, you find a linear resistivity. And this, I don't want to claim that this totally understood, especially in the whole dope case. Okay, there's another I don't know why I skipped like 5 transparencies here. Okay, there's another quantum critical point here where instead of being linear in temperature, we get the power 1.6 here at the end. The quantum critical point now is between superconductivity and a Fermi liquid, and this is not understood with this power law. Yes?
SDW, which became a superconductor.
Yes.
Yeah. So what is the nature of the transition from SDW to superconductor?
You're asking if it's first order or second order. Well, I mean, in some cases, there's even coexistence here between antiferromagnetism and superconductivity. In that case, I think that it's all second order. but it could be first order. And there's nothing theoretically that forces it to be second order. Okay, now this anti-ferromagnetism has something to do with the pseudogap on the electron dope side. So again, we are here, and there's a line that I call pseudogap. So I will explain what the pseudogap is. So this is the Fermi surface of an electron dope cuprate, and I have to explain that we're looking at zero frequency. In other words, we're looking at the Fermi level. And if I looked, I was plotting the non-interacting Fermi surface. It would be these arcs here. In fact, it's a single. If you look around pi, this is just a simple, just a circle. Now the color plot is, so this is ky and kx. You have guessed, and the color coding is as follows. It's the probability that an electron at this momentum has zero energy. That's it at the Fermi level. So here, if it was non-interacting, everything would be red here. Now it's not the case. This is red, and now this is blue, means that the probability of having an electron there is very low. The experiments that measure this are angle resolved photoemission spectroscopy. So it's called ARPES. It's just Einstein and Hertz photoemission, except it's resolved in angle. So in the electron dope cuprates, you can understand what is happening as follows. This is the antiferromagnetic wave vector, pi. So this, as a function of temperature, this pseudogap appears when the antiferromagnetic correlation length is of the order of the thermal de Broglie wavelength. And this was verified experimentally. So this is the color code here is the size of the correlation length. So red means like 400 here. Here is 2 or something. And this is where the pseudogap appears. And you see that it does not appear when the correlation length is equal to 2 or 3 or anything. I mean, it can occur here when it's 50. So, so the important thing is that it scales like the thermal de Broglie wavelength. And the thermal de Broglie wavelength is just what you learned in elementary statistical mechanics. There's an uncertainty in energy that you take equal to kBT. And this uncertainty in energy is equal to V Fermi times uncertainty in momentum, which is h bar delta k. And you transform delta k, the uncertainty in wave vector, into 2 pi over the thermal de Broglie wavelength. So the thermal de Broglie wavelength in dimensionless unit is just Vf over T. So this is the distance over which the electron remains coherent thermally. Let me skip this. And the physics of this is simple to understand. Why we get we get this pseudogap? It's because in 2 dimensions we have long-range order really at 0 temperature only because of the Merman-Wagner theorem. So at finite temperature, nevertheless, we have leftover, if you want, of what would be the mean field transition. So when the correlation length is larger than the thermal de Broglie wavelength, and you look at all the phase space, it's true only in 2 dimensions, in other words, you see that you get a precursor of the 0 temperature states, even in the normal state. So at high temperature here, you have the energy as a function of wave vector is just around the Fermi wave vector is just like this. But then in the ordered state, at the antiferromagnetic zone boundary, there's Bragg reflection, and then a gap opens up. So, so in other words, you remove states from the Fermi level. Now, if you're in this intermediate region here, this pseudogap region, when you are at the intersection with the antiferromagnetic zone boundary, you remove weight and you put it elsewhere. You know, it's not at the Fermi level. It's now lower or higher. So this is how we get you get this. Okay, so yes.
Can you comment a bit more why is it specific?
Yeah, I can do it on the board. It is just a phase space argument. So and another way to say it, I'll do the mathematics later if you want, because it will take me some time, but it's not really very complicated. But what I want to say is that one way, let me go back. Oh. It seems that this is going forward instead of back. Okay, now I'm. Okay, one way to understand this is that in 3 dimensions, this mean field thing, in 3 dimensions, when the gap, when you reach the transition, the gap is 0. But in 2 dimensions, when you reach the transition, which is here, the gap is already finite. So there's a whole range here where you can go sort of open up this gap. So that's one way to see it without the math, but I can show you with it. And you can do detailed comparison. If you look at these calculations with the Fermi surface plots, it is okay. So I would claim that in the electron doped cuprates, we understand this pseudogap phenomenon. They are very simple in some sense. There's superconductivity, there's anti-ferromagnetism. I will come back to the superconductivity later. Now the anti-ferromagnet itself. So this is this region of the phase diagram. So again, there are emergent properties. So there's broken symmetry here. There's time reversal symmetry and translation by 1 lattice spacing are broken. But if you put the 2 together, then they're not broken. Now their collective modes are a consequence of this broken symmetry. So there are spin waves all the time. And there's a single particle gap. But if you look now at there's a difference whether the anti-ferromagnet comes from a Mott insulator or it comes from an ordinary metal. If it comes from an ordinary metal, it's called an itinerant anti-ferromagnet. Otherwise, it's called just a Heisenberg anti-ferromagnet. And the differences can be seen like this. Both of them have spin waves. All these emergent properties are there, but the ordered moment will be different. The Landau damping will be different. The spin waves will go all the way to J if you're in an Heisenberg model, but not if you're in an itinerant system. And in the normal state, they're even more different. In 3D, they're metallic if they're weakly correlated, or insulating if strongly correlated, and the pressure dependence of the Néel temperature is different. So let me rephrase this. So this is temperature as a function of interaction strength in a cubic lattice at half filling. Now there is a line I will describe here in a moment. Here, this is the so-called Slater mechanism. So it's nesting or just perturbation theory or RPA, give it the name you want, but this is how the transition is described. You go from a metal to an anti-ferromagnet. In this side, you come from an insulator to an anti-ferromagnet. So here you have local moments. It's very different. Now this is the Mott, what's left from the Mott transition. So there's a non-trivial physics that goes on here because you need to go from a metal to something that has local moment at finite temperature. Now, what dynamical mean field theory has shown us is that if you remove this, theoretically, you can remove this transition if you want, and then look at what would happen to this line. It would go, if you extend it all the way to 0 temperature, you get a mean field description, a dynamical mean field description of this line that Antoine will tell us about. That goes from metal to insulator. Now the spin waves in the high temperature superconductors, this is done on a whole dope cuprate, are given, let's say, by these dots here. That's the experiment. And the line is the calculation. And what you see is that if it was purely Heisenberg model, here it would be flat. There's a small dispersion. And this small dispersion comes from the fact that you get 40 square over u only if u is very, very, very large. Otherwise, you get corrections in the higher powers of t over u. So you get these so-called ring exchange terms and longer range hopping. And from this, you can find that the value of U for the whole dope cuprates is of order 8 to 10 times hopping. Yeah? Yeah.
So, referring to what you said before, if you were more in an incident regime, you would not expect the spin wave branch to be well defined all the way to
That's right.
incredible
Yeah.
range, 200 millielectron volts.
It would hit the particle-hole continuum at some point.
You would have Landau damping that would broaden this thing,
Yes.
which would then get lost in
I
the
mean,
continuum.
asymptotically here, you always have them.
Sure, of course.
But eventually,
So here, 300 millielectron volt is really J or...
yeah. Well, yeah, J is 125 millivolts, and that's 2J. Yeah.
So the ring exchange value that you calculate, is that consistent? For example, you can get the J from, you can get the U from two things, right? You can get it from the slope, or you can get it from that.
No, unfortunately, you cannot get U from the slope here. What you can get is only 4T square over U.
Yeah, 4T square over U.
So you need to have an independent estimate of T.
Oh, right.
Okay, so you can take from band structure, but if you want to stay within purely T experiment, then you need to fit the whole spectrum to extract T and U independently.
I see.
And in fact, T prime and T double prime. Okay, so in the whole dope cuprates, this is what I just showed here. In the anti-ferromagnet, or the lightly doped anti-ferromagnet, you get well-defined spin waves. Here, you are in a regime where in this region, they are incommensurate. In other words, they're not quite at pi, and they have this hourglass shape. In this region, we'll talk about it later, there's a charge density wave, and the spin, but they're still at high frequency. There's still some spin excitations that are relatively well defined. In the superconducting state, there's a resonance that appears here that I will show you on the next slide. So it's a busy slide, and it's not really so important for our discussion, so I would spend too much time. But this is we are scanning this way here. So the red line is scanning like this. So now I centered the Fermi surface around pi, so it just looks like some square or some rounded square. And so this is H here is like that, so you get the red here, the green there. And if this axis is energy. So you see in the superconducting state, you get this resonance at 40 millivolts. And you remove the states here because you've opened a gap. So contrary to the case where you have electron-phonon interaction, there's little feedback of the electrons on the phonons. There is. It's not zero, there is, but it's small. Here it's relatively important. You remove the low energy spin waves. The superconducting gap does. Okay, now the charge density wave state. So let's look at the whole dope again. So we're focusing on this region of the phase diagram now. Evidence for something strange happening in this region came from experiments from Louis Taillefer in Sherbrooke on quantum oscillations. So they just measured the Hall effect in France, in Toulouse, as a function of a magnetic field. And you see that the Hall resistance at high field here has oscillations. Again, this just comes from the quantization of orbits, and it was understood by Onsager. And what's remarkable is that if you look here at the low temperature, this is this region here, where you see the oscillation. You see the sign of the Hall coefficient is negative, and that means that the carriers are electrons. And I've been talking to you about holes all the time. So there's, as a function of temperature, there's a reconstruction of the Fermi surface. There's a phase transition. And so the Fermi surface includes a small electron pocket. Now in 2013, one can do much better with the C-axis resistivity, the Nernst effect. These oscillations are seen everywhere. And Marc-Henri Julien in France pointed out through NMR experiment that there was a field-induced charge order in this region in 2011. And since that time, there's been a flurry of experiments. I cannot quote everybody, but here is just really X-ray scattering. And they saw peaks that appear at a wave vector really like an order parameter. So they found a transition. Here, this is this CDW. And the spin waves are in this region. So here there's some spin excitations at low frequency. Here it is a charge order that occurs in this region. And T star, so the pseudo-gap temperature, I will talk about it later. Again, in the all dope cuprates, is not where this transition occurs. But it could be a precursor in the same way as I had in the case of anti-ferromagnetism. Yeah.
For a long time, experimentalists generally used to claim that the charge density waves were seen only in La2CuO4
yes.
doped, and almost all other materials there was no evidence for that.
Yes.
Suddenly you see a flurry of things. What has changed? I mean, like, are they? I mean, you know, it's just.
Yeah, it's a very good question. Yeah. So in LSCO, in lanthanum copper oxide, these are really stripes. And in other words, you have a charge and spin at the same time. Here it is different. It is really charge only, no spin modulation. Now, why did it take such a long time to see? Well, there are two reasons. One is that there's been a great improvement in resonant and elastic X-ray scattering and X-ray measurements in general. And the other reason is that phase space is huge. So, I mean, the Q and the intensity is very, very weak. You have to remember that X-rays scatter off all electrons. And here you want to focus on just the few electrons that are happening on the Fermi surface. So it takes very, very high precision. And you sort of need to look where to look. You need to know where to look in the Brillouin zone. Yes?
So what is the structure of the CW in terms of like a Q vector, and does it change as a function of doping and temperature and so on?
Yeah, very good question. This is the Q vector is here, and this is as a function of hole concentration. So you see that it changes a little bit, and it's different from LSCO. You see, LSCO is here. And this is what you would expect from naive arguments, where you take that this, these stripe discussion that were going on for a long time, it would be 2 times 1/8. So it is not quite this, you see. It grows as an order parameter. The temperature dependence you're asking grows as an order parameter. Now, people have done ultrasonic experiments and to decide if it's a biaxial order or if there's a single wave vector, and I'm not sure of what the final word on this is, but I thought it was more like biaxial. It's like there are waves like this and waves like that, but not one plus the other that gives a single wave vector like this. You see what I mean? Yes, it can form domains, and
to have one of the leading experimentalists, Mathieu Le Tacon from
Mathieu is
Max
there.
Planck, Stuttgart. Who is
yeah, so you can ask him all these questions, and he will give you real answers instead of trying to fake your way around like I do now. So now this is the relation of this wave vector with the Fermi surface. So this is the non-interacting Fermi surface, and this wave vector is close to what is observed experimentally, but, well, actually it's a factor of 2 or so off, almost 3. Now, if you just look, if you remember, well, I showed you the picture for the electron dope. For the whole dope, it's this piece of the Fermi surface that disappears. So if you just just get rid of this piece and look at this, you get closer to the actual value. And in fact, if you put back the broadening that comes from interaction, you get something that's pretty close. So it looks as if it comes from, in a weak coupling picture, it would come from an enhanced susceptibility in this direction. But in fact, you need to have first neighbor, second neighbor interaction. It's not clear what this is. And also there are, the modulation does not coincide with the, it looks like the modulation is on the bonds instead of on the copper itself. So let me leave this to Mathieu. You can ask him all these questions.
The short answer you are giving here is that the way that stability does not seem to follow simple nesting in the hold-up case.
Right. You need to do something funny. You need to put in the interactions, get rid of some part of the Fermi surface, and then keep only. So it's, yeah, that's right. The end of the arcs. Yeah. Yeah. So what is the pseudogap in the whole dope case? So now we go back to this and we ask the question, does it have anything to do with being a precursor, or is it something else? Okay, so it turns out that if you do just simple Hubbard model calculations, this is the experiment, and this is the calculation. And this is the same as this, but as a function, the time here is like energy. So as you move close to the Fermi surface, we'll start this again. How come it's... If you look at this, you will see it looks as if the spectral weight here is pushed back when you see it becomes larger, but when you reach the anti-ferromagnetic zone boundary, it's pushed back. But and this is the case of the electron dope within the same calculations. So it looks as if the anti-ferromagnetic zone boundary has something to do with it, but it is, all these calculations are for short range. So there could be another mechanism which has to do with strong coupling. And in particular, why it is not a simple precursor can be seen by looking at the temperature dependence as a function of temperature. So this experiment is the night shift measured by experiment. So the night shift measures the uniform magnetic susceptibility. So if you have a non-interacting system, you can just use the Lindard function, or if you want, it's perturbation theory, there's the denominator, and here you just make sure that there's electron and hole. And in this case, you see that when omega equals 0 and q goes to 0, this is a derivative of the Fermi function. The integral just gives the density of state. So in the non-interacting case, or the Fermi liquid, you expect a constant on the scale of the temperature that's on the scale of the Fermi energy. Now, the experiment is quite different. The experiment was first done by Alul. And the point is that you see that the night shift here, this is the compound that's right above at the doping where the charge density wave occurs at the highest temperature. So this if we call this T star, you see that the night shift seems to have a strong temperature dependence before we hit the charge density wave transition. This was the measurements of Henri Julien. And now with these more recent experiments, this is shifted up here. And so there's a factor of 2 here. And there are other experiments I will talk about here in a moment. So there seems to be evidence of a real phase transition here, but this T star occurs way before this transition occurs. And this is just to show that it's possible within the cluster dynamical mean field theory to get these strongly dependent night shift. Okay. Now, this pseudogap temperature was seen also in transport measurements. So this is a plot of, this is data by Ando. And what is plotted here is the second derivative of the resistivity. at every temperature. So you take a curve here, resistivity as a function of temperature. At every point, you compute the second derivative, and you make a color plot. And you see that so people call the pseudogap this deviation from linearity. Linearity here means white. Second derivative is 0. And then it curves like this, and then the other way. So it changes from blue to red. And this is where you would see deviation from linearity in the Nernst coefficient divided by temperature. So in the Nernst measurement, what you do is you put a temperature gradient, and you measure the transverse voltage in the presence of a magnetic field. So it's sort of a Hall effect induced by thermal motion. And so you see that the Nernst coefficient occurs basically where the uniform magnetic susceptibility was going down. And the charge density wave transition is here again. It's quite separate from this. Now these are other experiments for the same compound, the same doping, this doping here, where the transition is at 150 Kelvin, where they have measured now the leading edge shift of the RPS measurement. So in other words, there is this removal of weight from the Fermi surface, and you look where it first appears. That's called the leading edge. So as a function of temperature, these are the this is this scale here, and this is in black, I think. I forget the. And then okay, so this is the RPS measurements, and well, the final result is one of the lines here. I forget which one. And then the other experiment is transient infrared reflectivity. And the third experiment is the Kerr effect. So what is the Kerr effect? You send polarized light, and then it comes out with the polarization that is shifted, that is rotated a little bit. So you see that there seems to be a real phase transition at this point, and we know now that it corresponds to this charge density wave. Now, I won't go through this just to say one thing. It's just that there are signatures of this charge density wave in transport measurements. They were first suggested, in fact, by transport measurements. These are these experiments of Taillefer I mentioned earlier. And these same signatures are seen in this one-layer compound that's mercury 1201, because the yttrium barium copper oxide has 2 layers, 2 copper oxygen layers per unit cell. And then people are always worried that this is sort of an artifact of this bilayer thing. But even in single layer compound, you can see these effects. Yeah, not that I know of. I mean, specific heat, for example. Yeah. They're big. Big background to subtract, and so it's hard to tell. I'm sorry. In some ways, I prefer the other sign with temperature. It's getting really hot here. So. Okay, the last statement that I'm going to make, which is a little bit disconnected, is to say that the pseudogap does not come from superconducting fluctuations either. For example, there are these experiments of Alloul, Rullier, Albank, and Riken that looked at the phase diagram as a function of disorder. Now they added another variable. And clearly, TC depends a lot on disorder, but the pseudogap itself is very much independent of disorder. So that's one indication that pseudogap and superconducting fluctuations are different. This is another experiment that gives the same answer. This is torque magnetometry, so you measure the diamagnetic susceptibility. And for mercury 1201 is you have the TC that is like this, and you can see signs of diamagnetism just above this. This is this color plot. And if you look at these other compounds, so BISCO and LSCO, then the TC is like this. And again, you see signs of diamagnetism just above the transition, very close to the transition. Okay, now another complication. In reality, we have copper oxygen, as I said. So if you look at, this is a picture from scanning tunneling microscopy from the group of Seamus Davis at Cornell. And I don't have time to go through all the details, but the point is that you see that there seems to be some intra-unit cell order, and that's along the bond. So they seem to imply the oxygen. So all the discussion I had before, at least theoretically, it was in this one-band Hubbard model. Here, if the oxygens are really playing an active role, it means one needs to take a more complicated model. And another example where one would need to take a more complicated model is to explain these experiments. In fact, the theory came first by neutron scattering, where they look at polarized neutron scattering. And they looked now not around pi, but around q equals 0. So it's translationally invariant. Yet they see an onset that looks like a phase transition. And it's supposed to, what is ordering now is within a unit cell. You see this is a unit cell. And what the theory proposes is that there are loop currents within a unit cell. And this is where the phase transition occurs. So these would like to say that the pseudo-gap in the whole dope is a real phase transition. It has to do with these loop currents. If it's the case, again, the one-band Hubbard model is not appropriate. Now, some experimentalists I talked to are not convinced by these experiments. Again, these are very small signals and so on, but, well, we need more confirmation. Okay, I finished now with superconductivity. And now some general statements first. There's a discussion to do which is similar to what I did between weakly and strongly correlated antiferromagnets. So in the case of superconducting phase, there are properties that are the same, whether it's weakly or strongly correlated, whatever. So the emergent properties, they have the same broken symmetry. The broken symmetry is this charge conservation, or U1 for S wave. In the case of a D wave superconductor, you also break the rotation by 90 degrees. There's a single particle gap. And depending on the type of order, whether it's S wave or D wave, you have point or line nodes. And that will determine immediately the temperature dependence of the specific heat, the thermal conductivity, quantities like that at very low temperature. And also the Goldstone modes. Now, if you want to look in more details now, not only at asymptotically low energy, but in more details, now you need to worry about the model and non-universal properties. BCS is has universal ratios, for example, delta over KBTC. And we would never know the mechanism for sure if you had only BCS in some ways. But at strong coupling, with if you're familiar with Eliashberg theory, then you see, by looking at the frequency dependence, that you can see signatures of the presence of phonon. So it's deviations from BCS that really tell us the mechanism in detail. Well, so the high temperature superconductors, the first thing to say is that they are D wave. So D wave means that the Cooper pair has this wave function has this dependence. So it changes sign. So there are nodes along the diagonal. And the experiments that showed this the most convincingly are interference experiments. So you look at the Josephson junction. Okay, if you're not familiar with this, don't worry. I mean, the only thing you need to know is that it's D wave. So here is just a single ordinary Josephson junction between an S wave and a D wave superconductor. And if you look at the magnetic field dependence of the critical current, it should look like a Fraunhofer diffraction pattern. So this is what you see. Now, if you do a corner junction, now I have a D wave and I have S wave. Then there's plus, minus. So there's already a current that is circulating, even in the absence of a field. And you see that the Fraunhofer pattern is shifted here. So this is one, I mean, really an interference experiment that shows that there are not only nodes, but also there's a change in sign of the wave function. And these are even more detailed experiments that were done later by Tsui and company, where they look at tricrystals. So in the absence of a magnetic field with a squid scanning probe, they were able to show that there's a spontaneous current explicitly. And here, if you're in one of the crystals, or at the interface of one of the two crystals, then there's no spontaneous current. Okay, so there are two laws that were proposed, and I don't know if they are emergent properties or not. And there's still, that's still a mystery in some ways. I'm supposed to tell you what is the mystery. So one of them is Ohm's law, not the usual Ohm, but another one. So if you look at the spin stiffness, not the spin, the superfluid stiffness. So this is related to the penetration depth as a function of the DC conductivity times Tc. Then you see that this is quite impressive. You have 10 to the 2 here and 10 to the 9 here. So you have 7 orders of magnitude. And these are all layered superconductors. And these layered superconductors, they all fall on this law. So this is proportional to this with the power law 1. If you just look at the dimensional analysis, you realize that it corresponds to assuming that at Tc, the scattering rate, scattering time is h bar over temperature over kBt. Sometimes people call that Planckian diffusion. At Tc. And here is the superfluid penetration depth as a function of sigma dc, and it's along the c axis. And the power law now is to the minus 1/2. It is less convincing, I mean, but it's still many decades, but this is larger and so on. Okay, back to this. So if we talk about the superconducting state, one of the questions is whether this is going down because of these orders, or if Mott physics is enough to do this. In other words, what is under the dome? So let me switch back to some theory a little bit. So first I talk about the weakly correlated case. How do we understand D-wave superconductivity if you come from an itinerant antiferromagnet? So this was proposed before the advent of high temperature superconductors. I mean, this paper is a collaboration between Sherbrooke and Arce, was the first one. And if you look at the BCS gap equation, one way to understand what's going on is like this. Let's talk about the usual case first. So the usual case is that the gap is independent of direction. So it's a S wave. Now this factor here is positive because E is a positive number, so the Fermi function is less than 1/2. Now this is the effective potential that could come from phonons. So in the case of S wave, if this U is attractive, if it is attractive, then it means you have a minus sign, and then there's get rid of this minus sign, and there's a self-consistent solution. If U is positive, then everything else on the right is positive. And then there can be no S wave solution because you have a positive number equal to a negative number, or negative equal to positive. Now the way around this is if there is some momentum dependence in the wave vector, in the gap. Suppose I look at the gap in the direction P here. And suppose that this is peaked, this is very large at pi. So it means that the dominant term in the integral here will be, for example, when the term that goes from here to here. So it will be a P prime that's connected to P in this way. So in that case, if the gap changes sign for P prime, then I can have a solution, even if U is positive. Because if the gap is positive here, and P prime is negative, so when this is large, then I have positive equals positive. So this can be done much more rigorously with I guess Zanke and Schultz at ORC were the first to do this with the functional renormalization group. There's some weak coupling perturbation theory. And it's a two-particle self-consistent approach that satisfies Merman-Wagner theorem. Here I just flashed some comparisons for the D-wave susceptibility computed from Quantum Monte Carlo and with this approach, just to show, just to benchmark the approach. You can get a TC that has this, dome shape. And the reason for the dome is that in this region, there's a pseudogap comes in, so you remove states from the Fermi level, and then pairing becomes less efficient. So I would say that from the point of view of theory, much is understood in the case of this weak coupling point of view. I don't claim that there's detailed comparisons with experiment with electron dope, but it's sort of the next step to do. Okay, now the other correlation that is seen experimentally is that the linear, the slope here of this linear dependence, so you have some number times temperature for resistivity as a function of temperature. The value of this coefficient, the slope here, goes to 0, where Tc goes to 0 in the overdope case. And this correlation has been seen also in the one-dimensional organics and in the pnictides. So this seems to be a strong correlation. In the two-particle self-consistent approach, we don't quite have that, but we do have a decrease of the linear coefficient. Now, the last point is the strong coupling point of view. So this is what should apply to the, I think, to the whole dope case. So a cartoon strong coupling picture is as follows, and it goes back to Anderson, not in 2007, but way before that, in 1987. And in fact, it was proposed before the ITC by Schmidt-Rink and Varma. If you just take the Heisenberg model and you write the spin operators in terms of fermions, you see that you can have anomalous pairings like this. And if you work out the sign, you find that if you look this as a D-wave order parameter, you find that the sign is negative, so it's attractive. So already at mean field, it looks as if you could have superconductivity. This is credited by Anderson to Pitaevsky and Bruckner. In other words, the pair state is orthogonal to the repulsive core of the Coulomb interaction. That's why you get D-wave. So in the talk that I will give at the workshop, I will describe in particular what I call strongly correlated superconductor and show some differences between strongly correlated and weakly correlated. In strongly correlated case, Tc does not scale like the order parameter. The superfluid stiffness scales like doping. Superconductivity can be largest close to the metal insulator transition. And there's a resilience to nearest neighbor repulsion. Okay, so I have a few slides on the view from dynamical mean field theory. I'm not supposed to do this here, so perhaps I will keep this for the workshop. And here I just want to advertise that there's a summer school that we organize in Sherbrooke next summer on computational methods for quantum materials. So you can register on the net if you're interested. There are a few scholarships that are available. So I will answer questions and yes?
Sir, at the beginning of your slides, you said that there are some broken symmetries in the system. How the time reversal symmetry is broken in the superconducting state?
No, not in the superconducting state, in the anti-ferromagnet. It can be broken. There are some broken symmetry, time reversal symmetry states for superconductors, but not in the high temperature superconductors as far as I know. So, although some experiments claim there is, but I don't think it has been shown convincingly. So in the case where time reversal symmetry is broken for a superconductor, you could have, for example, dx squared minus y squared plus I dxy.
P plus IP.
Or P plus IP, yes. Here it is definitely singlet pairing, so it cannot be P plus IP, but it can be D plus ID or D plus IS if you want, or something like that. So when the order parameter is complex, you break time reversal symmetry. Yes.
Another question: for strong coupling superconductors, does the disorder has any other effect other than this pseudogap? Any special effect? Disorders plus strong correlation?
Yes, there is a very strong resilience to nearest neighbor repulsion that is not found in the weak coupling case. And this TC does not scale like the order parameter. And this is more like, I don't have any theory behind this now, but this is more like speculation.
Thank you.
Actually, it's an experimental observation, which I like to attribute theoretically to the strongly correlated case. There is a little bit of ambiguity in the vocabulary because we are used to talk about Eliashberg theory as a strong coupling. But from my point of view, Eliashberg is still weakly correlated. It's strong coupling with the phonon, but weakly correlated. So sometimes I say strong coupling superconductor, but I don't mean Eliashberg. I mean strongly correlated. So U is important. All this Mott physics is important.
In one of the first slides, you showed the photoemission spectra double peaks, and you said it was from Mott transition and not from the semiconductor, because semiconductor also had was expected to have 2 peaks. So how can you say that it's from Mott and not from?
Okay. So in the case, as you said, in the case of the semiconductor, I also have 2 peaks because I'm starting from a very deep level, and then I can excite an electron here or there. So that gives 2 peaks. But if I look at the cross-section, it should, with doping, this should be independent of doping, and this should grow linearly with doping. Okay, here I just remove one electron to show the effect. In this case, this goes down with doping, and this goes up twice as fast with doping. And this is what we see here in these curves. So at half filling, there's only one bump. And if it was a semiconductor, that bump would stay the same. And there would be another bump here that would grow linearly with the doping. Here instead, this bump is going down, and the other one is going down linearly with doping, and this one is going out twice as fast, twice the doping. Actually, when I say 2, it's not exactly 1 or 2, but the point, I mean, qualitatively is clear what happens. And as I say, if you can do some Hubbard model, okay, these arrows show where the weights are coming from, right? It's coming from there, it's coming from there. And if you look at cluster dynamical mean field theory, this solid line is what you would expect for the weight of this lower peak. And the experiments are all these scattered points here. And now this group that published this PRL first said, well, this is inconsistent with the Hubbard model. Here it is. And now here it should be flat. But in fact, if you look at the error bars, the black line fits just as well in the single band Hubbard model. Does that answer your question?
Yeah. And one more thing, how is the correlation or coherence length calculated through experiments?
Okay, the correlation lengths that are shown were anti-ferromagnetic correlation length. So the way you do that experimentally is that you measure the neutron scattering cross-section, and from this you extract the spin-spin correlation function. And you look as a function of wave vector, and then the half width at half maximum is a measure of the inverse correlation length. So it's a rather direct measurement. All the form factors are known because this is just dipole scattering, dipoles of the neutron scattering of dipoles of the spin, so it's quite accurate actually. You don't know the absolute value, but you certainly know the widths and so on are fine.
And there was one figure which states the disorder dependence of the TC, the
Yes.
fall of TC.
Mm.
What is the percentage of fall with disorder? Is it quite drastic or?
Well, it's a D-wave superconductor, so it's quite sensitive toward disorder. An S-wave superconductor is not, actually. It's Anderson's theorem, it's called, because you just pair time reverse states. But here, even though you pair time reverse states, there's a sign change when you scatter, and that sort of mixes plus and minus, and it destroys superconductivity. So I don't have the numbers in my mind, but I've seen curves that come even within ordinary BCS theory. You look at D wave and S wave, and there's a huge difference. Like the S wave will go like this, and the D wave will found very quickly with disorder. So, but it turns out that anyway, the high temperature superconductors are surprisingly resilient to disorder. At the beginning, people were using this argument to say it's not D wave because we see that it resists to disorder.
The dip in the superconducting dome, is that accepted to be a universal feature? Is it seen in all cuprates?
Excuse me, I did not understand.
The dip in the superconducting
Oh, the dip, yeah. Yes, so the dip, as you saw, comes from the charge density wave, because we have the charge density wave right there.
So it is...
So in LSCO, you don't see that dip, but it's quite, the charge density wave, or in that case, is stripes, and it is not, here the charge density wave is here. In LSCO, as soon as there's stripes here. When I say stripe, I mean charge and spin density wave sort of together. And so there are stripes here, and then there are stripes that they just change direction when you get from here to there. I forget which direction it is, but they just change direction. So they start right from here. So there you don't see this dip. In the mercury compound. I think we can look at the plot. I showed the picture of this. Sorry, you're certainly dizzy with all this. Okay, it's coming. Oh no, okay, it was before this. Yes. Okay. Well, I forget where the plot is. I think there is in the mercury compound. Yeah, you see, this is YBCO, and this is mercury 1201. And even though it is a single layer compound, you see there's a small dip here. And if you look at the transport measurements, they're all the same signatures that the Taillefer had seen here appear here. So it seems that at least in two compounds, there's this small dip, and it seems to be related to charge density waves. And the charge density waves don't seem to help superconductivity. They really compete.
The origin of the superconductivity, excuse me, sir. The origin of the superconductivity is not understood yet, is that?
Well, I mean, within weak coupling calculation and within cluster dynamical mean field theory, the single band Hubbard model does give D-wave superconductivity. But what we are left with, really to convince everybody that everything is understood, is to have material-specific predictions instead of just, okay, we see a TC. It's actually the TC that are found are like 200 Kelvin instead of 100. That's fine because fluctuations will move that down and so on. But if we had some material dependent predictions. Yes. Yes.
Let's say from the strong coupling cluster DMFT point of view, the origin is clearly J. So it's a vindication of Anderson's and whoever original ideas.
Yeah.
the weak coupling, it's also spin dances,
Yes.
spin correlations,
Yes.
right? So I wouldn't say it's not understood. I would actually
No,
say
no, no.
it is understood.
Yeah, that's what I was trying to say, that it is understood, but that not everybody agrees with that.
Yeah.
And that the way to convince everyone is to have material-specific prediction.
So in that context, can you comment on Laughlin's recent paper?
Yes, I can comment on Laughlin's recent paper. He's a friend of mine, and I don't. I hope you don't quote me. But I mean, he ignores everything about the Mott transition. So all these things I showed to you that prove that this is a Mott insulator, he cannot explain it within his theory. He's trying to explain everything just from R3 Fock and some emergent properties of various phases. Okay, his mechanism is different. I mean, in this case, it is the nearest neighbor. I mean, there's a term that is if you start from a microscopic theory that includes all the bands and everything, and you take the most general thing, there are terms that are correlated hopping terms. So where hopping depends on, he claims that the Mott, there's no such thing as a Mott insulator. Well, there is, I'm sorry, experimentally you can see systems that are insulators and don't have any long-range order. And I guess that Laughlin doesn't want to call a phase something that does not exist at 0 temperature. But here, to describe all these crossover at finite temperature, you have a mean field theory that goes all the way to 0 temperature. Okay, you might never see that state because some long-range order will come in, or perhaps there won't be some long-range order if you have a spin liquid. But still, Laughlin doesn't want to, doesn't like the Mott insulator. Thank you very much.